So after talking about communication systems and sampling and reconstruction of signals, that was our communication application. Let's move our attention to some control systems applications. So feedback in control systems, stability in systems. So in order to address those applications, as well as filter design, we would need Laplace transform. And we'll spend some time talking about why Laplace transform, why do we need Laplace transform in the first place, and then we'll talk about properties of Laplace transform and some examples, just as we did with Fourier series and Fourier transform. A lot of the properties that you will find in Laplace are going to appear very similar as you did in Fourier transform, because they are there's not a very significant change. There are some changes, of course, and we'll talk about those. But in terms of properties, many of them will look very similar to Fourier transform properties. So let's start talking about the two-sided Laplace transform and the region of convergence. Now, there was no region of convergence discussion during Fourier transform. We just said, all right, if there is a Fourier transform that exists, if the signal is integrable or square integrable, if the signal has certain properties, then the Fourier transform will exist, and we will be able to find that Fourier transform using properties or the definition of the Fourier transform. And in fact, we use some other tricks as well to find the Fourier transform of signals. Now over here, when we talk about Laplace transform, we will need to talk about two things. One is the transform and the other is the region of convergence. Both combined will give you the Laplace transform of a signal. So we'll spend some time talking about why we need to talk about the Laplace transform, some motivation behind Laplace, and why is it different from the Fourier transform that we saw earlier. So in order to do that, let us take a look at a very simple example of this signal u of t. So you have a unit step signal over here, which is not square integrable. In fact, it's not even absolutely integrable, which means that if you take a square of this, so if you take the absolute of the signal and you square it and you integrate it for all time, you will not get a finite value. If you take the absolute value of it and you integrate over all time, you will not get a finite value, because this is unit step and it is going to be 1 for all time. As you keep integrating, that area under that curve will keep increasing. Whether it be the absolute area or the square of the area, it will keep increasing, which means when you do the integration over all time, it will not be a finite value. That's a problem. So even though we have found the Fourier transform of unit step using some tricks, we used an exponential function and we evaluated time tending to 0. So we used some tricks in order to find the Fourier transform of unit step. But if you look at the Fourier definition, cap x of omega is defined as negative infinity to infinity x of t e to the minus j omega t dt. That's the Fourier transform definition. Now, if we apply that definition for unit step, u of t is only defined for time greater than 0. So this integration modifies to 0 to infinity 1 multiplied by e to the minus j omega t dt. And that is a function that does not converge, because if you integrate that exponential, substitute the limits, you will see that that does not converge. That is going to be infinity. But if we use a trick here, suppose we borrow a factor e to the negative sigma t, where sigma is a real positive number. So for example, e to the minus 5t, e to the minus 10t, e to the minus 50t, something that decays exponentially, and multiply our signal with that. So instead of considering the Fourier transform of u of t, now we are considering the Fourier transform of e to the minus sigma t u of t. So essentially we are saying that let us put a damping exponential on top of our unit step, so that when we do the integration, our area will converge. Right? So that's essentially what we are doing. We are borrowing a factor e to the minus sigma t, where sigma is a real positive number. Now we are evaluating the Fourier transform of a new signal, which I'm going to highlight in yellow. That one. Earlier, I was just trying to find out the Fourier transform of u of t. Now I'm trying to find out the Fourier transform of e to the minus sigma t u of t. Now this guy will exist because now it is square integrable, which is a harder, which is a stronger condition of existence of Fourier transform. This, what is this? Well, I can write this as Fourier transform of a new signal, which is x of t e to the minus sigma t. Right, x of t in our case is unit step here. So when the summary is, if the Fourier transform of a signal does not exist, we may be able to make it converge by superimposing or multiplying it with a damping exponential e to the minus sigma t over here, where sigma is a real number, real positive number, e to the minus 5t and so on. Now, you might ask a very fair question here. Why did we choose only a real value for the exponential? Why didn't we choose sigma to be a complex number? Why did we choose sigma to be a real number? And the answer to that is, if we chose sigma to be a complex number, it would have some real part and it would have some imaginary part. But the imaginary part, something written as e to the jx, does not contribute to the magnitude. So it will not help with the convergence of that integral. The only thing that will help in convergence of that integral is a positive number for sigma, a real number for sigma. Because if it was imaginary, it would just merge with that exponential, and that doesn't give you any magnitude. All right, it looks like my WebEx is again. Are we back? Okay, it looks like we are back. So that's the reason why we choose sigma to be a positive number, as opposed a positive real number, as opposed to a complex number. If it is complex, like I said, it will contribute only to the phase. It will not contribute to the magnitude, and we are trying to make that magnitude converge, so it will not help us in that way. So coming to the third point over here, which is we extend the Fourier transform by first borrowing that factor e to the negative sigma t, where sigma is a real positive number. This is valid for causal signals, that is the signals that are 0 for time less than 0. So we are going to borrow this factor e to the minus sigma t in order to help make that integral converge. But we can't just borrow things, we'll have to return them later on. So let's take a look at all those manipulations on this slide here. So procedure for transformation, meaning procedure to borrow, then take the Laplace transform, and then after you take the inverse borrow, take the Fourier transform, then when you're doing the inverse transformation, you have to calculate the inverse Fourier transform and then return the borrowed factor in order to cancel out the first borrowing. So procedure for transformation. So we are trying to talk about multiplying the signal with that e to the negative sigma t, then finding out the Fourier transform. Those are the two steps listed over here. That evaluates to calculating integration negative infinity to infinity x of t e to the minus sigma t. So that's the signal for which we are trying to find the Fourier transform. And we applied the Fourier transform integral, so it appeared with the e to the negative j omega t dt. Oh, dt is missing here. And we are going to define that as cap x of omega, but now it also depends on sigma, so we are going to include that in the argument as well. So cap x now depends both on omega and sigma. Omega is the radian frequency and sigma is the Neper frequency. That's the real part of that exponential that we borrowed. Now we can rewrite this integral in a very nice form, which is negative infinity to infinity x of t, the signal of interest, multiplied by e to the minus sigma plus j omega t. And we can define sigma plus j omega as our complex frequency variable s. That will give us this first identity in the red box here. Cap x of s, the Laplace transform, the two-sided Laplace transform of x of t is negative infinity to infinity x of t e to the minus st dt, where s is defined as sigma plus j omega. Sigma is, let us write that over here. Sigma is the real part of s, and omega is the imaginary part of s, where s is this complex frequency variable. Next, how do you do the inverse transformation? Well, first calculate the inverse Fourier transform, then you return the borrowed factor. In other words, you multiply with e to the plus sigma t. So we can do both these steps right here. This is where we are multiplying with e to the sigma t, and the rest of it is the inverse Fourier transform definition. And the inverse Fourier transform is with respect to omega. So 1 over 2 pi, omega goes from negative infinity to infinity, x of omega comma sigma e to the j plus j omega t dt d omega. That's your definition of inverse Fourier transform. Now, if you simplify this a little bit, you will get 1 over 2 pi, omega going from negative infinity to infinity, x of omega comma sigma, and now you can combine e to the sigma t and e to the j omega t and write it as e to the st instead, d omega. Now, all of that can be written in this boxed red box over here as the signal in time domain can be calculated, can be evaluated by finding out the inverse Laplace transform, which involves 1 over 2 pi, s goes from sigma minus j infinity, and s equals sigma plus j infinity. Now, why are we writing the integration limits with respect to s? Because we are integrating with respect to s, and only omega is going from negative infinity to infinity. Inside the integral, what do you have? You have the Laplace transform x of s, which in other words we wrote as cap x of omega comma sigma, and e to the st, which is what? E to the sigma plus j omega t. So all of those are being used from the earlier step over here. So you have in the boxed step, in the boxed results, we have how do you find the two-sided Laplace transform of a signal given the time domain information, and how do you find the inverse Laplace transform given x of s. Now, in this discussion, we have assumed that sigma is a real positive number. So far we have avoided the very detailed conversation on region of convergence. So this x of s, even though it has an equation, it also needs ROC, region of convergence information. For this particular discussion right now we are having, sigma is a real positive number which defines our region of convergence. That's where the integral is going to converge. If sigma is not a real positive number, then the integral will not converge. All right. So the next obvious question is, if I chose sigma to be a real positive number, will it converge or not? In more general, a more generic question would be, does this transform integral converge at all sigma and all omega? And in order to understand, in order to answer that question, let us consider the Fourier transform of x of t multiplied by e to the minus sigma t. So what we are doing is x of t multiplied by e to the minus sigma t. We are looking at, does that converge for all real sigma or not? And the specific x of t we will consider, to keep things simple, is u of t. Now, your x-axis is time, your y-axis is u of t multiplied by e to the minus sigma t, where sigma is a real value. In order to answer that question, let us consider both conditions. One is sigma is less than 0, and the other is sigma is greater than 0. So in the red case, you have e to the minus negative value for sigma t, which essentially makes it e to the 5t, 10t, right? So essentially that makes it increase exponentially with time. And hence the color choice of red, danger, is not going to converge. is going to grow, explode with time, right? So if sigma is less than 0 in this case, x of t multiplied by e to the negative sigma t is neither going to be square integrable nor it is going to be absolutely integrable, right? So notice over here you have a negative sign in the exponent, and on top of that you have a negative sigma, which makes that exponential function increase with time. The red one, right? Just for the sake of clarity, I hope you guys realize that is one, right? Now, if we chose sigma to be greater than 0, a real positive number, what would happen? You would get e to the negative 5t, e to the negative 10t, something that decays exponentially. That is multiplied by u of t, of course. So if sigma is greater than 0, x of t multiplied by e to the negative sigma t is going to be both square integrable and absolutely integrable. As you can see, as I scan from left to right here, my area is going to converge to a particular value. It's going to be less than infinity. So what is this? This is the signal multiplied by the borrowed factor. In other words, we have tried to answer the question, does the Fourier transform of x of t multiplied by e to the negative sigma t converge or not? And the answer, by looking at these two, is if sigma is greater than 0, it will converge. If sigma is less than 0, it will not converge. If you have a decaying exponential, it will converge. If you have a growing exponential, then it will not converge. So you have to choose an appropriate value for sigma in order to make that integral converge. The part of the S-plane is a complex plane like this. You have sigma, which is the real part of S on the x-axis, and j omega, the imaginary j multiplied by imaginary part of S on the y-axis. That's your complex S-plane. On the complex S-plane, we will try to sketch, three things essentially: poles, zeros, and the region of convergence. Those three things need to be sketched on the complex S-plane, because that gives us the information about where does this integral converge, where are things going to be stable or not. So that gives us a lot of insight into what type of system we are going to be coming up with. So where is the region of convergence? We said sigma should be greater than 0. So as you can see here, sigma, which is the real axis, greater than 0. So everything to the right side of the vertical axis is shaded in green, indicating that is the region of convergence, or ROC. So that is the part of the S-plane where that integral, what is that integral? Negative infinity to infinity x of t e to the negative sigma t and multiplied by e to the negative j omega t dt. That integral is going to converge, which we also can write as integration negative infinity to infinity x of t e to the minus st dt, right? That's the same as that. So this integral will converge as long as sigma is greater than 0 based on this particular discussion there. So I've drawn the ROC to the right side of the vertical axis, indicating all indicating the region for which sigma is greater than 0. So let's try to recap here. The part of the S-plane where the integral converges to a finite number is called region of convergence, which is ROC, shaded in green over here, right? So green things over here in this particular slide and in general here, I will use green to indicate things are stable, things are moving in the right direction, things will converge, right? If that is true, then I need to change the color of this to black, because that has nothing to do with it. So for u of t, the ROC, that's the signal for which we are sketching the region of convergence, right? So u of t. For the signal u of t, region of convergence can be sketched as all that green shaded region over there. But for some reason, I put one pole here. So I said in the complex S-plane, we need poles, we need zeros, we need ROC. We already sketched ROC in green, and I have indicated that I have one pole over here and I have no zeros. Zeros are indicated by drawing circles like that, and there are no circles drawn on this S-plane. So I've indicated that there is a pole at 0 when S is 0, and there are no zeros in this complex S-plane. And on the next slide, we will talk about where that pole comes from. How did we get that? On the next slide, I'll try to take a look at that. Now, pole is the point in the S-plane at which the integral actually goes to infinity. So that's not included in the ROC. That's a very important point. Poles are never included in the ROC. Zeros may be included in the region of convergence, but poles are never included in the ROC. Poles are indicated by X, zeros are indicated by 0, and region of convergence is essentially a shaded by shading, like we shaded in green. All right, so region of convergence is to the right of the pole in this case, right? And it so happens that our signal u of t is also right-sided. U of t is 0 for time less than 0, and then as soon as time is greater than 0, it is present. So we are going to come up with a classification later on where we'll classify this as a right-sided signal, and you will see that for right-sided signals, the region of convergence will be to the right of the rightmost pole. More about that later. But I hope you see that it is right. The region of convergence over here is right of the pole. So next, let us take a look at why is the pole there, and we'll talk more about the shaded region as well. Okay, so the first example of Laplace transform. Find the Laplace transform of u of t. So let us define the time domain function f of t as u of t. By using the definition of the Laplace transform, we can say Laplace transform of f of t equals negative infinity to infinity u of t e to the minus st dt, where s is defined as sigma plus j omega, the complex frequency variable. Now u of t is going to be 0 for time less than 0, but it is going to be 1 for time greater than 0. So I've modified the integration limits based on u of t. E to the minus st dt remains as is. This is the exponential function which can be easily integrated, and then you substitute the limits. Now what you have here is negative 1 over s e to the minus st, where t can be infinity or t can be 0. So notice what is going to happen. If you plug in infinity, you will get e to the negative s times infinity, which is going to go to 0, right? Oh, sorry, the e to the negative st, that is going to go to an infinity. But if you make the real part of s to be greater than 0, that is the only case where it will converge to 1 over s. So if you plug in 0 here, this will be plus 1 over s, but it will go to infinity if your real part of sigma is less than or equal to 0, right? So real part of s is less than 0, and you have a negative sign there, which will make that exponential have a positive exponent, which will make that go to infinity. So what does that mean? That essentially means that if the real part of s is greater than 0, that integral is going to converge to 1 over s. And if real part of s is going to be less than 0, you will have negative multiplied by another negative over here, which will correspond to e to the positive exponent. And of course, time is positive here, so that will make it grow with time, and the integration will not be finite. So by using these two, what do you have? 1 over s, that's the Laplace transform. Where is the denominator going to 0? When s is 0. That's how you get a pole over here. So the values of s which make the denominator go to 0 are the poles in the system. So there is only one pole over here, and the pole is at s equals 0. So that's how you mark the x at origin. And the green region is what? Real part of s, sigma greater than 0. So everything on the right of the pole we have marked as the region of convergence. So both these combined, the Laplace transform of the signal, which is 1 over s, and the region of convergence, which is sigma is greater than 0, or real part of s is greater than 0. Both those combined give you the complete Laplace transform information of the signal. So both things are required. What is the function in the S domain and what is the ROC? All right, questions about this example here? Take the function, put it in the Laplace transform equation. We have already discussed why we need e to the minus st, why we need the real part. We are using that to make the integral converge, and it will only happen for certain real numbers. It may not happen for all the real numbers. And then once you come to this particular point, how did you derive 1 over s and infinity again? All right. So let us try to take a look at that step. So what is that going to equal? I'm just plugging in the values there. Negative 1 over s e to the minus s infinity, right? Minus of minus plus 1 over s e to the minus s times 0, right? From this is where I'm going from here to here. All right, I'm going to come to Jacob's question in just a minute. So this is pretty simple, right? This one will go to 1 over s. Fine. But how about this guy? Time is positive, right? 0 to infinity, time is positive. And if s has sigma plus j omega, right? The j omega part doesn't contribute to the magnitude. So if I just assume this to be sigma for now, what would happen? So here you have negative and a sigma and a very large number. If sigma is negative multiplied by negative, what is going to happen? You are going to get infinity over here, right? You see why you got that infinity when sigma is greater than 0? When it is less than 0, what is going to happen? When it is less than 0, it will go to infinity. But if it is greater than 0, you will have negative, positive value, and a very large value. So all of that will tend towards 0, right? So you will have 0 plus 1 over s instead. All right, now let's come to Jacob's question. Something I've never completely understood is what a pole really is. Well, a pole really is a point in the S-plane where things go to infinity, right? Where the response does not converge. So I understand that it is in context of filters, it represents a 3 dB correction on your Bode plot. So in context of filters, all right. We are jumping many lectures here, but suppose there is a band pass filter, right? And you need that particular frequency to pass through. I can make the system go to 0 here. So I'll put the zeros over there in the blue places, and I will put a pole over here. So if I put two zeros here and here, and the more zeros I put over there, the better it is. And if I put a pole over here in frequency, what is going to happen? It will be 0 here, it will go to infinity here, it will go to 0 here. That means that I can choose the location of poles and zeros in order to adjust the frequency response of my filters. If you want certain frequencies to pass through, at that place, put a pole. If you want certain frequencies to stop going through, put zeros over there. That's where the system will go to a 0. We are going to have a much more detailed discussion on filters and poles and zeros and all of that later as well. But yeah, that's exactly how they relate to that. So if you want a bandpass filter of a certain this kind of transfer function, I'm going to choose to put one or maybe more zeros here and here, and I will put a pole there. Shouldn't there also be a similar bound on j omega? Well, there is not going to be on any bound on j omega, because what is this? What is absolute of e to the j omega t? That's always 1, right? So the magnitude of a complex exponential never contributes to the magnitude. The only thing that contributes to the magnitude, or the growing aspect of things or decaying aspect of things, is e to the sigma t, the real part of s. That's the only thing that contributes to the value converging. E to the j omega t or e to the j5, e to the j10, those are going to be things that contribute only to the phase. But that doesn't have anything to do with convergence, right? That's why there's no bound on j omega. All right, let's keep moving. A new signal, e to the minus at u of t, where a is a real number. A belongs to the set of real numbers. E to the minus at u of t can be plugged into our Laplace transform just as we did earlier. Now u of t is going to be 0 for time less than 0, so we adjust the limits there. We combine the exponential functions here. You have minus a here, minus s there, so you can combine them into one exponential function as e to the minus of s plus a times t dt. Again, can be integrated very easily. Exponential functions are easy to integrate. You integrate and you have the limits again. So what are you trying to do here? Well, you are trying to make it converge. When you are trying to make it converge, you essentially want this guy, well, actually you want the entire thing to be positive, right? You want, so if the blue highlighted one is positive, then e to the negative x will be smaller, right? What does that mean? That means I want s plus a times t to be greater than 0. T is already greater than 0. How do you know that? Well, look at the limits. Infinity, 0. So t is already greater than 0. So I don't need to worry about t. I need to worry about s plus a. If I want s plus a to be greater than 0, I really mean I really want sigma plus a to be greater than 0, because j omega doesn't contribute to the magnitude. So that's how you get s plus, so that's how you go to the region of convergence. You have to look at the exponential being decaying or growing. And it also depends on t, right? So if your the integration limits were negative, then this condition would be reversed, right? But because t is positive and you want your exponent to be negative so that you have a small number, a converging integral, then s plus a should be greater than 0. J omega doesn't matter in this case, so sigma plus a should be greater than 0. In other words, you can also rewrite this as sigma, real part of S, should be greater than negative A. Right. Again, the color choice, green and red for converging and not converging. So combining all of this, you get the Laplace transform is 1 divided by S plus A, and the region of convergence is defined as real part of S, which is greater than negative A, like we just said. Okay, so we found out the Laplace transform of u of t. We found out the Laplace transform of e to the at u of t, where a is a real number. Both these cases had the function in the S domain and also had the ROC mentioned. Next, let us take a look at Laplace transform of negative e to the minus at u of negative t. Again, a belongs to the set of real numbers. Similar process, take the function in time, put it in the Laplace transform, Laplace integral, negative infinity to infinity, e to the minus negative e to the minus at u of minus t e to the minus st dt. Use u of minus t. What is u of minus t? It is going to be a flipped version of u of t, meaning it is defined only between negative infinity and 0. At that time, it is 1. Simplify, write it as 1 exponential, integrate, you get 1 divided by s plus a multiplied by e to the minus s plus a times t. Now take a look here. You want this to be positive, right? Same thing. You want the blue highlighted part to be positive, so that you get a e to the negative positive number. But t, where is t? T is actually doing negative, right? The time actually is negative. What does that mean? That means I need s plus a to also be negative, right? If I want s plus a to be negative, then you have a negative there, negative there, negative there. 3 negatives will make a negative. So you will have a smaller and a converging integral. S plus a needs to be negative. J omega doesn't matter. So sigma plus a needs to be negative. In other words, sigma should be less than negative a. So the real part of S should be less than negative a. Where is the, what is the Laplace transform here? 1 over S plus a. So you got 1 over S plus a with the region of convergence being real part of S less than negative a. Questions about these two examples, e to the negative at u of t and negative e to the negative at u of minus t. There is a particular reason why we have chosen these two signals, and we will talk about that in just a bit. Okay, so you know, the signals are easy enough to do the integration. What is crucial over here is how do you find the region of convergence? And I hope that I have conveyed, you know, how to you know, piece out each and everything that is happening in that exponent and where you want it to go. In the region of convergence, you want to make it converge. So you want e to the negative 5, e to the negative 10. You want that exponent to be decaying. If you want that to happen, and you are, so there are 3 things to it. This is positive or negative, you have to evaluate that, right? Next is s plus a positive or negative, you have to evaluate that. And t is positive or negative, you have to evaluate that. So all those 3 play a role there. All right. Next, let us take a look at the results of the previous 2 examples that we looked at. The previous 2 examples were e to the negative at u of t and e to the negative at u of minus t. So where a is a real number. For both of them, we had the same Laplace transform. F of s was the same. 1 divided by s plus a for both of them. However, their region of convergence was different. So that's another possibility. 2 signals can have the same Laplace transform, but they might be different in terms of where they converge. So for the first signal, your region of convergence was real part of S is greater than negative a, and for the second one, real part of S was less than negative A, where A belongs to any the set of real numbers. So that's another thing to note. So, which raises a question: what if you were asked to find the inverse Laplace transform of 1 over S plus A? Would you say that inverse Laplace transform of 1 over S plus A is this in blue or this in green? Which one would you say? Well, clearly they are different in terms of their region of convergence. So you would have to take a look at where is that integral converging. So you have to talk about the region of convergence. So you would say 1 divided by S plus A, the inverse Laplace transform of that would be e to the negative at u of t, the blue one, if the real part of S is greater than negative A. It could also be the other one, negative e to the minus at u of minus t, if real part of S is less than negative A. Which means that you cannot just simply give me the function in the Laplace domain, you also have to give me the region of convergence in order for me to tell you what is the inverse Laplace transform. Questions about this? Now, a quick question is, we wanted to sketch things in the S-plane. Why didn't we sketch things over here in the S-plane? The reason is we are using an arbitrary real arbitrary real number in A. So I can assume A to be 1 or negative 1 and then do a sketch, but because A is a arbitrary number, arbitrary real number, that's the only reason why I didn't do a sketch. If I assign a constant to it, a real constant to it, then I can do the sketching. I would also like to point out this. E to the negative at u of t is a signal that moves to the right, right? So it does this. And the other guy, it goes to the left. So the signal that is right-sided has a region of convergence to the right of the pole, and the signal that is left-sided has a region of convergence to the left of the pole. So keep that in mind as we go through these things. All right. Now, in the previous two problems, because I had A as a arbitrary real number, I could associate a positive value with it and a negative value with it. So I'm writing a table over here with A being plus or minus 1. So those two results have become 4 things now. E to the minus t u of t, negative e to the minus t u of minus t, u of t, e to the t u of t, negative e to the t u of minus t. So all 4 of them have a certain f of s and a certain ROC. For the first two, the function in Laplace domain is 1 over s plus 1. And for the next two, the Laplace domain is 1 divided by s minus 1. And they have their own regions of convergence. So let's see. 1, 2, 3, and 4. Can you guys pick one of them, and then we will talk about its S-plane. Pick one out of the 4, and we will draw the S-plane information for that. All right, Eric says 1. Let's do 1. I am sketching the S-plane for 1. I've got sigma on the real axis. I've got j omega on the y-axis. Where is the pole? The pole is, where does the denominator go to 0? s plus 1 has to go to 0, so s has to be negative 1. So the pole is at negative 1, marked by a cross at negative 1. Then my region of convergence is real part of s greater than negative 1. So I would draw a vertical line, an imaginary vertical line, maybe in a light gray, right here. And then I'm going to shade in green, say, everything to the right, without including that imaginary line in gray. I am staying away from that gray line. I hope you see that. I cannot include that line because that's where the pole is, and at a pole things go to infinity. So that would be my region of convergence. So I've marked the pole, there's only one pole, and I've marked the region of convergence. Everything to the right of that vertical line. That vertical line is what? The vertical line is sigma equals negative 1. And then, in a similar fashion, you can sketch for 2 and 3 and 4. I've just sketched it for 1. We have noted this earlier, but it is worth noting again. Laplace transform of x of t is defined by both x of s and its region of convergence. Now let's take a look at an interesting example here. Two different signals with the same transform but different ROCs. So you have Laplace transform of negative u of t as negative 1 over s. Why? Because Laplace transform of u of t was 1 over s. We derived that earlier. If you multiply the signal with negative, your Laplace transform also becomes negative. So Laplace transform of negative u of t is negative 1 over s with a region of convergence as real part of s greater than 0. But for u of minus t, it is also the same function, negative 1 over s, but in this case, the region of convergence is real part of s is less than 0. A right-sided signal first, left-sided signal second. Same Laplace transform, different ROCs. Next example, find the Laplace transform of t times u of t. So you have the function in time domain as t times u of t. You plug it in our Laplace integral formula. You have negative infinity to infinity t times u of t e to the minus st dt. There is a u of t, so that you can use that to leverage to adjust your limits of the integration to be 0 to infinity. T remains as is, e to the negative st. Now you can integrate that using product rule of integration or whatever integration strategy you want to apply. But if you integrate that, substitute the limits just as we have been doing so far, you will get that result to be 1 over s squared, and it will converge to that only when the real part of s is greater than 0. Now what do you have? Laplace transform of t u of t is 1 over s squared with the region of convergence to be to the right of the pole. Actually, you have two poles here, right? So I should probably just say two poles here at 0. Two poles at 0 because you have 1 over s squared. So they are repeated roots there. S equals 0. And everything to the right of that pole is in the region of convergence. So that would be the Laplace transform of t times u of t. Okay. Next, what is the Laplace transform of an impulse function? Similar deal. Plug that impulse in our Laplace integral. You have integration over all time delta of t e to the minus st dt. You have a delta of t multiplied by e to the st, so using the properties of impulse, what is that? That is simply delta of t multiplied by e to the minus s times 0, which is what? It is simply delta of t. And you are integrating for all time, which means you are integrating over that impulse to give you a value 1. And this is independent of s actually, right? There's no denominator, there's no pole, which means that it will converge for all s. So set of complex numbers. The region of convergence is the set of all complex numbers. It will converge everywhere. Now here is probably one of the most interesting examples we have seen so far. Here you have a signal that is not just right-sided, right? The right-sided part is being highlighted in yellow. It's moving to the right. And there is also left in blue. So it's actually a two-sided signal. Because it's moving to the right and it's also moving to the left, so it's a two-sided signal. E to the minus absolute of t. The sketch is provided over here, that which is, sketching it is not a big deal, but finding the Laplace transform and more importantly its region of convergence is a big deal for this example. So let's take a look at that. You have x of t as e to the minus absolute of t. X of s, the Laplace transform of x of t, can be written as negative infinity to 0 e to the plus t e to the negative st dt. And for the positive time, you have integration from 0 to t e to the minus t e to the minus st dt. The reason we have broken up into these two integrals is because the shape of the function is different because of that absolute of t. So it's different for time less than 0 and it's different for time greater than 0. When time is less than 0, the function is actually e to the t, and when the time is greater than 0, the function is actually e to the minus t. So we have taken care of those two things over here by evaluating, by splitting up that Laplace integral into two integrals. Now if you do some manipulation on the first integral, what do you have? Integration from over negative time e to the 1 minus s times t. So how would you qualify? Can we go from this integral to writing this statement? Can we say that? Can we go there? Let's try to take a look. I am going to write that in maybe blue. My time variable is negative. If I have my time variable to be negative, in order for me to make this converge, I would want 1 minus s to be greater than 0, right? If 1 minus s is greater than 0 and time is negative, then this will converge. In other words, 1 minus s is greater than 0 also means that 1 minus sigma, right? Sigma is what contributes to the magnitude, should be greater than 0. Or sigma should be less than 1. That's how we get to this. Right? So you have to evaluate where is the time. Time is negative between negative infinity and 0. Then you evaluate the coefficient of t, the limits on the coefficient of t. All right, let me erase this and let's go back. Okay. So that's how you get the region of convergence here. Now let's do the same thing for the other piece. You are integrating over positive time, right? So if this is positive, but there's a negative sign here, so you would want s plus 1 to be greater than 0. Or I should say real part of s plus 1 to be greater than 0. So sigma plus 1 should be greater than 0, which means sigma should be greater than negative 1. Now take a look at this. The region of convergences, actually let me color code this. For the right-sided signal is yellow, right? So this should be yellow. And for the left-sided piece, I have blue here. when you evaluate the integrals, they come out to be 1 over s minus 1 for the first integral and 1 over s plus 1 for the second integral. However, their region of convergence are different. For the left-sided piece, it is to the left of the pole, and for the right-sided piece, it is to the right of the pole. So 1 divided by s minus 1, there is a pole at 1, because when s is 1, the denominator goes to 0. So there is a pole at 1. And for the second piece, which is 1 divided by s plus 1, there is a pole at negative 1. So you can combine that and write it as one rational function here, which is 2s divided by s squared minus 1. However, you see over here, region of convergences are different. So our overall signal, how should I sketch the region of convergence for that? Well, the key word over here is that the region of convergence is going to be the intersection of the individual regions of convergences. So if for the left one, right, where are we sketching the pole here? See, left one was, I believe left one was blue. So let's use blue. There's a pole at 1, right? And the region of convergence is to the left of that. So it's this way. Too big? Maybe this is fine. And for the other piece, yellow, you got 1 over s plus 1 here. And that's how we know that it is negative 1 there, the pole. But its region of convergence is actually moving this way. So the intersection of those two regions of convergences is the region of convergence of x of t, the overall signal. And if you see this, the blue arrow and the yellow arrow only intersect in that region shaded in green, excluding the poles, by the way. So you are excluding the lines. What is that line? Oh, it's really, it doesn't include sigma is negative 1 and 1. So if you have a couple of things we can note here. If the signal is two-sided, then the region of convergence is turning out to be a vertical strip in the S-plane. It's a strip, right? It's bounded on both sides. So if it's a two-sided signal that is not bounded on either side, in the S-plane it is actually bounded and it happens to be a vertical strip. And the region of convergence for any signal is actually the intersection of all the regions of convergences in that signal, which make up that signal. Right? So the intersection of regions of convergences is what we are after. Questions about this example? All right, let's start talking about the properties of Laplace transform. A lot of it is going to, again, look similar to Fourier transform properties. If you have two functions, f1 of t and f2 of t, whose Laplace transforms are given as f1 of s and cap f2 of s, and their regions of convergences in the S-plane are defined as r1 and r2. And if you have a and b as scalars, then a times f1 of t plus b times f2 of t is going to have a Laplace transform as a times cap f1 of s plus b times cap f2 of s. And the region of convergence of the new signal a f1 plus b f2 is going to be r1 intersection with r2. That's your intersection sign. This is actually what we did in the previous example as well, while we were doing the e to the minus, so on the left-sided exponential and the right-sided exponential. So now let's take a look at this example here. We are trying to find the Laplace transform of 2 delta of t minus 3 u of t plus 4 t u of t. We are trying to find the Laplace transform, which means that we need to find the function in the S domain and ROC. So for 2 delta of t, from a previous discussion, delta of t, the Laplace transform was 1. 2 delta of t, the Laplace transform is going to be 2. What is the region of convergence for a delta function? We said region of convergence, well, instead of writing ROC, we'll just write real part. Real part, no, it's all right. So ROC belongs to set of real numbers, set of complex numbers. All complex numbers, yes. Next, minus 3 u of t. So that will give you minus 3 times, for u of t we had s divided by s. What was the region of convergence there? It was a real part of s greater than 0. Next, plus 4t u of t. That is simple, plus 4 divided by s squared, and the region of convergence for this guy as well is going to be the same, real part of s greater than 0. So all complex numbers greater than 0, greater than 0. The intersection of all those three regions is going to be real part of s greater than 0. So for that, I am going to say the ROC is real part of s greater than 0. That's the answer. So I can manipulate the functions to write it in different forms, but that's essentially my answer. I've got the function in the s domain here, 2 minus 3 divided by s plus 4 divided by s squared. I have noted their individual regions of convergences. I have found the intersection of all those regions, and that gave me my region of convergence for the overall signal. Real part of s greater than 0. Next, a time shifting property. If f of t, the Laplace transform of f of t is f of s, and the region of convergence is R, then if you shift f of t by t0, then the Laplace transform of the time shifted signal is going to be e to the minus s times t0 multiplied by f of s. Very similar to what you saw in the Fourier transform properties. When you shift a signal by t0 in the Fourier domain, you multiply by e to the minus j omega t0. That's exactly what we are doing here, except our functions are slightly different. We have a complex frequency variable instead. So the proofs of these properties are going to appear very similar to what we have done before, which is why we are not doing it again. And when you shift things in the time domain, left or right, obviously you are not changing the ROC, right? Because there's just delayed one over the other. It has nothing to do with where the integral converges, because it involves only a time shift, delay or advance. It doesn't change the region of convergence. Now let's take a look at the Laplace transform of u of t minus 2. So for u of t, right, for u of t, the Laplace transform of 1 was 1 over s with sigma greater than 0, right? The real part of s greater than 0 was the region of convergence. Now when you shifted the signal by 2 units, u of t minus 2, you delayed it by 2 seconds, then that 1 over s got multiplied by e to the minus 2s. So let us highlight this 2 caused that. But the real part of s greater than 0 did not change. There's a comment on the chat box. So j omega never altered the region of convergence. Absolutely right. A region of convergence is never a horizontal thing. It will always be a vertical thing. You got it? Yes. Because j omega, e to the j omega, only contributes to the phase. It never contributes to the magnitude. So I don't even need to consider that in growing or decaying aspects of an integral. So you could always draw the ROC on one-dimensional line instead of the complex. Yes, you could, but there are other reasons why we draw it in the S-plane, because it will later come into picture. Right now, you are right. It's only a one-dimensional thing. But we want to take these things that we learn here and apply that to stability and feedback and systems. So we will need this S-plane. All right, let's move on here. Okay, so we have another example here, which is an interesting looking function. It has some linear aspect to it and it has some rectangular aspect to it. We are trying to find the Laplace transform of this function. So the first thing that I'm going to do here is write the function in terms of unit steps. So I'm going to straight away do this because I think that you guys will be able to do this without any problem. The function is going to be t minus 1 between 1 and 2. So t minus 1 multiplied by u of t minus 1 minus u of t minus 2. So open the gate at 1, close the gate at 2, and multiply that function with u of t minus 1. So that piece, yes, let's do yellow there. That is that. Next, you have a rectangle that opens the gate at 2 and closes the gate at 4. U of t minus 2 minus u of t minus 4. So this guy is going to be that guy. That's it. Now, if you simplify this a little bit, you can write this as t minus 1 u of t minus 1 minus t minus 2 u of t minus 2 minus u of t minus 4. Now, this is in a very good form and we can write the function in the S domain. Next, f of s. The first one is going to be what? T, so t u of t shifted by 1, right? T u of t is what? 1 over s squared. Delayed by 1 is what? E to the minus 1s. What is the region of convergence? Greater than 0, right? ROC, real part of s, greater than 0. Next, minus t minus 2 u of t minus 2. Same thing, 1 over s squared multiplied by e to the minus 2s now. And the region of convergence is going to be exactly the same. Paste it right here. Next, minus u of t minus 4. Well, that is 1 over s for u of t, and minus 4 gives me e to the minus 4s. And the region of convergence, still the same. So the overall signal, I can actually write the same thing for the overall signal, because it is the intersection of all those three. Questions about this example? All right. The next property that we are going to take a look at is the integration property. If you integrate the function in time domain, you actually divide the function by s in the frequency or the Laplace domain. We are not proving it over here because we have proved it for Fourier transform. Things are looking very similar. Earlier we were dividing by j omega. So there was a way to there was an integration property for Fourier transform. There's an integration property for Laplace. When you integrate a function from negative infinity to some stopping time t, the function we are writing as f of tau d tau, and in that integration in the time domain reflects in the Laplace domain as division by s. Now let's talk about the existence of Laplace transform. And this is kind of a question that you guys have been asking for a while. So let's address this formally right now. The Laplace transform of a function f of t exists if the function f of t e to the minus st is absolutely integrable. Why is that? It goes back to the strong condition of Fourier transform existence. We said if the signal is absolutely integrable, then the Fourier transform of that signal will exist. Now we are considering that signal multiplied by e to the minus sigma t, borrowed factor e to the minus sigma t, and that is what needs to be absolutely integrable now. So it's the same strong condition of Fourier transform existence applied for the Laplace transform. So as long as this function is less than infinity, I know that the Laplace transform is going to exist. Now e to the minus st can be broken up into e to the minus sigma t and e to the minus j omega t. And the magnitude of e to the minus j omega t is always going to be 1. That is why it doesn't matter to the convergence. You will only have absolute of f of t e to the minus sigma t dt to be less than infinity. That essentially means the convergence depends only on sigma, the real part of s. And that's the formal proof for that. It doesn't depend on omega. Now there are a few properties that are strictly for the region of convergence that we are going to go over here, that we are going to discuss over here. So there is going to be a little bit of math involved, but all that math has to do with the core of that math has to do with observing the exponent of that exponential function, e to the jx or e to the x. You want that x to be negative in order for it to decay. That's the core of all the math that you are going to see on the next few slides. Property number 1. In general, the ROC consists of vertical strips of S-plane. ROC depends only on sigma. We talked about that in just the proof of that is the previous slide right there. Convergence depends only on sigma, the real part of S. So that essentially gives us property number 1. ROC depends only on sigma. It does not depend on j omega. Now, when I say in general, I'm talking about a two-sided signal. A two-sided signal will have vertical strips. So that's the general case. In some cases, the ROC might be moving right of the pole. In some cases, ROC might be moving to the left of the pole. And in other cases, ROC might be the entire complex plane, as in the case of impulse. But in general, for a two-sided signal, especially, the ROC will consist of vertical strips. An example we have seen before. Note, the Laplace transform of u of t is 1 over s. That's represented as the rational Laplace transform. The pole is where the denominator goes to 0. So that's when s is 0. And obviously s equals 0 should not be in the ROC because that's where the function goes to infinity. So it should not be a part of the region of convergence. So property 1 essentially says that the region of convergence is going to be in general a vertical strip. It is going to depend only on the real part of sigma, and it has to exclude the poles of the system. Property number 2, the ROC should not contain any poles of rational Laplace transform. So if you are able to take a polynomial in the numerator, a polynomial in the denominator for the Laplace transform of a function, and that's how you represent it using rational Laplace transform, you find out the poles of the system, meaning the values of s for which the denominators are going to 0. Those poles should not be present in the ROC, because by definition ROC is the region where it should be finite. Poles are the points in the S plane where the function goes to infinity. So by definition they should not overlap. Okay, now let's define a new term here which is called the support of x of t, and it has to do with the time domain view of the signal x of t. The values of t for which x of t is not equal to 0 is called support of x of t. So for example, u of t, the support is t greater than or equal to 0, because for time less than 0, the function is 0. So the support, it is supported by t greater than or equal to 0. For u of t minus u of t minus u of t minus 1, the support is bounded on both sides, 0 and 1, because the gate opens at 0 and closes at 1. So the support is both bounded on the left as well as on the right by 0 and 1. Now let's talk about, in a formal manner, a right-sided signal, a left-sided signal, a two-sided signal, and a finite duration signal. So you have 4 possibilities for the signal type here. And all these 4 are looking at the time domain view of the signal. For everything here, the x-axis is time. So the first one is the right-sided signal. A signal is right-sided if its support is bounded from the left by some time t0. So for example, over here you have u of t plus 1, which is sketched this way. Actually, I can even write this, right? So the signal is bounded on the left, but it keeps going to the right. That is a right-sided signal. So it is bounded on the left, in this case by t0, and in this case t0 is -1. Over here, u of t sine t, what is that? It's a right-sided signal with a bound on the left as 0, right? So t0 is -1 here, 0 there. So it's bounded on the left by t0. The support is bounded by the left by t0, but it is not bounded by on the right. So that's called a right-sided signal, and it is pretty obvious, right? You would obviously call this a right-sided signal because it's moving to the right. You would obviously call this a right-sided signal. Now next, what is a left-sided signal? The story is reversed. A signal is left-sided if its support is bounded from the right by some time t0. So I've bounded it on the right by t0. t0 is 1 there. Cosine t multiplied by u of minus t, that is also bounded by t0. In this case, what is t0? Cosine t multiplied by u of minus t, what is t0? Someone, anyone? Cosine t u of t. Just sketch that signal in your head. Cosine t u of t. All right, cosine t. My expert drawing is going to be available here. Oh wow. Oh no. That is cosine t. And so cosine t in red, and in blue, let us sketch u of minus t. What is u of minus t? U of minus t is this. So when you multiply, absolutely right, when you multiply them together, all of this will cancel out, right? This will cancel out. You will only have things to the left. So it's a left-sided signal with the bounds, where is black? Negative infinity, comma, 0. Negative infinity, comma, 0. Yes, you got it. So t0 would be 0 in this case. So signal moving to the left, of course you are going to call that left-sided signal. Now, a signal that has a finite duration, that means it is bounded both on the left as well as on the right. A signal has a finite duration if its support has upper as well as lower bounds. So it is bounded on the left by t1, it is bounded on the right by t2. For example, like this, u of t minus u of t minus 3. So it is bounded on the left by 0. So t1 is going to be 0 here, and t2 is going to be 3 here, because u of t minus 3 is bounded on the right by 3. And in that case, that it's going to be called a finite duration signal. And for a finite duration signal, ROC is all of S-plane. Everything is going to be included in the region of convergence. Can you guys tell me why that is the case? If the signal is of finite duration, why is the region of convergence all of S-plane? Why is that? Its integral is constant. Yeah, exactly, right? So because the limits of the integral are defined by t1 and t2, it will always converge. So ROC will always be the entire S-plane in this case. All right, we talked about this. Let's talk about a few things that are kind of related, right? So if suppose you have a right-sided signal, so on the left here, all the x-axes are time, and there are 4 graphs. The first one is a right-sided signal. The second one is a left-sided signal. The third one is a finite duration signal. And the last one is a two-sided signal. It's moving to the left as well as to the right. Now, when you have a right-sided signal, the ROC will be to the right of the rightmost pole. So right of the rightmost pole. And if you have a left-sided signal, the ROC will be to the left of the leftmost pole. If you have a finite duration signal, then the ROC will be all of S-plane, and we talked about that. The integral will have to converge, right? Like it's a finite area here, so it has to be converging. And if it's a two-sided signal, then it will be a vertical strip. We have looked at an example of this with the e to the minus absolute of t case. So these are some ideas that will be very helpful going forward. Some of this we are going to prove in any case. All right, let's take a look at property number 3, which is a signal which is square or absolutely integrable and has finite duration has ROC of the entire S-plane. We talked about this. We have actually asked the question and you guys said integral is constant, but we are going to deal with that proof here very quickly. The proof is Suppose that x of t is such a signal and its support is contained in a comma b. So it is bounded on the left by time a and it is bounded on the right by time b. Then if you consider the integral a to b for all the time x of t is non-zero, the absolute of x of t dt will be finite and can be defined to be some constant m. Consider two cases. Sigma is less than 0 and sigma is greater than 0. If sigma is less than 0, we are saying that the signal will be absolutely integrable between the times for which it is defined, a comma b. And in order to do that, we are going to prove this by taking a look at two cases, sigma less than 0, sigma greater than 0. And it has to converge on both. Let's see. If it is, so you're integrating from a to b, you have absolute of x of t e to the negative sigma t dt. These sigma is a real quantity, so you can break that up into absolute of x of t e to the minus sigma t dt here. Now, your time is going from a to b. What would be the maximum value of e to the minus sigma t? The maximum value. Your time starts at a, your time stops at b, and you're integrating the function. Obviously, when you are integrating, you are accumulating, and this function is always greater than 0, right? So this guy is an absolute, so it's always greater than 0 here, right? So think about this. If you have, let's see, let me add a page here. If you do an integration exercise over time, doesn't matter where you start and stop. Let's say a is here and b is here, right? The function is doing this, right? Or doesn't even matter. The function is, say, doing this, right? If the function is doing this between a and b and you are integrating, you see why I put it all above 0? Because I'm doing absolute of x of t, right? That's why I put it all above 0 here. So I'm sketching absolute of x of t here. When you integrate between a and b, absolute of x of t dt, can I say that it is going to be less than or equal to a to b absolute of x of t? I also had e to the sigma. With that being b, because when I accumulate, right, when I accumulate here, what is the accumulation result going to look like? It is always going to be more and more accumulation, right? So it is always going to start here and accumulate there, right? It is always going to go up because I'm accumulating more and more area as I go from left to right. So the maximum value of this function will have to be at time cap b. Do you guys see that? That's how we are writing this. This is greater than 0. E to the minus sigma t dt will always be less than integration from a to b absolute of x of t e to the minus sigma at b, because b is the upper limit in time. This has to be the maximum then, dt. So this is true because for sigma less than 0, e to the minus sigma times b is the maximum of e to the minus sigma t over the interval a to b. So if we define that as m, that finite value be m, then this would be m times e to the minus sigma b. Of course, that is less than infinity, so it will converge. And now similarly, if sigma is greater than 0, our lower limit on the time is going to be dictating the maximum here. So for sigma greater than 0, e to the minus sigma a will be the maximum of e to the minus sigma t, because you see time is going from a to b, sigma is positive, and you have a negative on top of that. So a will dictate the maximum value over a to b, but also converging, m times e to the minus sigma times a. less than infinity converges. So for both sigma greater than 0 and sigma less than 0, the integration of the signal x of t e to the minus sigma t is absolutely integrable, which is essentially the check for whether Laplace transform exists or not, right? That's the check. F of t e to the minus sigma t dt has to be less than infinity. All right, there's a question on the chat box. Let us see. Does this mean that the inverses of functions with ROCs of the entire S-plane, inverses of the functions with ROCs of the S-plane always have bounded support? Absolutely right. Yes. You got it. If you see an entire S-plane as the ROC, that means it has to be bounded in the support. Property 4. If x of t is a right-sided signal and there is a line in the S-plane, sigma equals sigma 0, there's a vertical line in the S-plane. So it could be, so here, let me draw it here, maybe here. So here is your S-plane, and this line could be here or it could be here, anywhere, but this is j sigma and this is j omega, and if this is say a and b, this line is what? This is sigma equals a and this is sigma equals b. That's the S-plane, right? So actually let's just quickly change the color here to red. Right, so the red line is sigma equals a, the blue line is sigma equals b, and right now in our property number 4 we are looking at a line, a vertical line, sigma equals some sigma sub 0. So the property is, if x of t happens to be a right-sided signal, that means that it is bounded on the left, and there is a line sigma equals sigma sub 0 is in the ROC, then any other line sigma 1 with sigma 1 greater than sigma sub 0 is also in the ROC. All of this means one thing. If you have a right-sided signal, then the region of convergence will be to the right of the rightmost pole. But it's a different way of saying that. So if it's a right-sided signal and you have two lines, one is at sigma 0 and one is at sigma 1. If sigma 1 is greater than sigma 0, then sigma sub 1 will also be in the ROC. Meaning, if this was sigma 0 and this was sigma 1, then because it is a right-sided signal, I already claimed, which I'm going to prove here in a minute, that the region of convergence will be to the right of the pole, right? So if it's to the right of the pole, it's everywhere. And the region of convergence would include sigma equals 1 in this case, right? So that's exactly what it is saying here. Given sigma equals 0 is in the ROC, then any other line sigma 1 with sigma 1 greater than sigma sub 0 will also be in the ROC. Now to prove this, we are going to do this for t sub 0 less than 0, and then we'll follow the similar procedure for t sub 0 greater than 0. Let's start. Suppose your x of t is 0 if time is less than some time t0. That means it is right-sided. So it is bounded on the left by some time cap t sub 0. Then the integral e to the negative infinity to infinity absolute of x of t e to the minus sigma 1 t dt. What are we looking at? We are looking at the existence of the Laplace transform for sigma equals sigma 1. We can write this using the property of right-sided. We can adjust the lower limit of the integration to be t sub 0 to infinity, absolute of x of t e to the minus sigma 1t dt. Now what is going to happen for t sub 0 less than 0, right? This guy right here could be less than 0 or could be greater than 0. For less than 0, we are going to prove this, and then for greater than 0, we can also prove it, but with a similar procedure, which we are not showing here. So let's take a look at what is going to happen to that integral with t sub 0 less than 0. You have the integration from negative infinity to infinity, absolute of x of t e to the minus sigma 1t dt. We have already assumed that sigma sub 0 is in the ROC, right? We have assumed that. I can rewrite this integral into two pieces. T sub 0 is less than 0, so I can break this up into t sub 0 to 0 and 0 to infinity. I'm writing that integration into two terms, in two integrals. One is boxed in blue and one is boxed in green. So in order for the entire thing to converge, both the blue and the green have to converge. If sigma 1 is greater than sigma 0, that's the assumption that we are making here. If that is the case, if sigma 1, a vertical line at sigma equals sigma 1, greater than sigma 0, and integral of t sub 0 to infinity absolute of e to the minus sigma 0 t dt is finite. Can we assume that? Yes, we can assume that, because we have said the line sigma equals sigma sub 0 is in the ROC, so that has to be finite since sigma 0 is in the ROC. Then let's go back to the green term here, green box here. You have 0 to infinity, absolute of x of t e to the minus sigma 1t dt will be less than 0 to infinity absolute of x of t e to the minus sigma sub 0 t dt. Why is that? Sigma 1 is greater than sigma 0. So you have a more damping here as opposed to this, because your time is positive in that case. So because of time being positive and exponent being a bigger negative number, that means more decay for the same amount of time. So if this is less than infinity, the other guy also has to be less than infinity. So the green box term has to be finite. How about the blue box? Take a look at the integral t0 to 0, absolute of x of t e to the minus sigma 1t dt. So we are trying to figure out whether sigma 1 is in the ROC or not for times between t0 and 0. Look at that integral, t0 to 0, absolute of x of t. Now a little bit of a trick here to prove this. We are writing this as e to the minus sigma 1t is written as e to the minus sigma sub 0t multiplied by e to the sigma 0 minus sigma 1 times t dt. Multiply and divide by e to the sigma sub 0 t. That is going to be less than integration from t0 to 0, t sub 0 to 0, absolute of x of t e to the minus sigma 0 t multiplied by e to the minus sigma sub 0 minus sigma sub 1 times t0. Why is that going to be less than this? Because t0, for time less than 0, t0 will dictate the maximum value of the signal. We talked about that earlier when we talked about this, the second case, sigma greater than 0 here. The lower limit dictated the maximum value. That's essentially why, so by just plugging in the lower limit there, we know that that is going to dictate the maximum value there. Now what is this? If this is finite and that is finite, this entire thing will be less than infinity. So if this is less than infinity, then this guy will have to converge as well. So combining the two results, blue and the green box, sigma 1 is in the region of convergence. And you can do a similar procedure for t sub 0 greater than 0. All right. Now, what about a left-sided signal? What about the signals like u of minus t? Where is the region of convergence for them? How can we view them using the time domain view of the signal? let's take a look at this. You have u of minus t, and we have borrowed the term e to the minus sigma t here as well as here. They are moving to the left. They are both left-sided signals. When sigma is less than 0, there is a decay. As time increases, the value decreases. With sigma greater than 0, it goes up, right? So it explodes, it grows. The top function is going to be absolutely integrable and square integrable because that will lead to a finite area. The signal at the bottom is going to be not absolutely integrable, nor it is square integrable. So this is not going to be part of the region of convergence. So when sigma is less than 0, that's when it will converge. Sigma less than 0. What does that mean? U of minus t, the Laplace transform was 1 over s. Actually, it was negative 1 over s. So you had a pole at 0. And the region of convergence is sigma is less than 0. So that to the left of the pole. So for the left-sided signal, your region of convergence is to the left of the pole. And if there are more than one poles, it will be to the left of the leftmost pole because of this exact reasoning. What is the inverse Laplace transform? What is the Laplace transform of u of minus t? We looked at that, but there's a quick proof here. Use the Laplace integral. X of s is negative infinity to infinity, x of t e to the minus st dt. Substitute the limits for u of minus t, which are only for negative time. So negative infinity to 0, 1 times e to the minus st dt. Evaluate the integral, plug in the limits, and find out the region of convergence. The same sequence of steps. Minus 1 over s, e to the minus st. The limits of the integration are 0 to minus infinity. It will converge only when sigma is less than 0. And the value to which it converges is minus 1 over s. So there is a pole at s equals 0. Because of that pole s at equals 0, I should do a pink there. Pole at s equals 0, you got something there. The pole there. Where does it converge? Sigma should be less than 0. So it converges everywhere here. Pole is not included in the region of convergence. Sanders says, I think you got the transform e to the minus absolute of t wrong. Is that the case? Let's see. Why do you think that numerator should be a 2a? You mean right here? All right, let's see. S plus 1 plus s minus 1. Oh, it is right. Huh? Sander, can you, I mean the 1 over s minus 1 should be 1 over 1 minus s. You mean this piece? All right, let's take a look. We have all right, let me take a look at this in a little bit more detail and clarify. All right, it also looks like we are out of time. I'm going to stop recording here.